Everyone, I am Rohit Kumar Singh, a teaching assistant for the course Experimental Physics 2, and this is the 10th live session. And today I am going to discuss some more concept of optics. Basically, I'll recap some of the concept of diffraction grating and polarization, and then we'll solve some example problems. So let's start. So first, diffraction grating. So what is it? So diffraction grating is diffraction at n parallel slits, okay, and with same width and separated by equal spaces, okay. And this was first used by Fraunhofer, uh, and what he did was he placed large number of parallel wires very closely to each other at regular intervals. But nowadays, gratings are constructed by rolling equidistant parallel lines on a transparent material like glass with a fine diamond point. So, and these ruled lines are opaque to light, so and light won't pass through it, so it will act as a distance between the slits, because the white space between the two slits is just glass which is transparent to light. So this is known as plane transmission grating. uh, and there are other types of gratings like concave reflection grating and so on, but today I'll just talk about simple plane transmission grating. Okay, so it is something like this. So suppose these these are the rulings, okay, and which are opaque to light, and this open spaces between them is the glass which is transparent light. So suppose a beam of light, parallel light is coming like this. What will happen is, so you have to think of it as n diffraction uh, points, okay. And so the Fraunhofer diffraction concept that we discussed last time will apply here also, okay. So we can, so what happens then, we divide the slit into two parts and we uh, perform the calculation to get the position of maxima and minima, right? So now here will be, here that we have n slits, so there will be n such calculations, and but all of them will behave same. So suppose if this diffraction angle is theta here, then here also we will have theta, and so on, okay. And suppose we have a screen here where we want to see the pattern, okay. So at p0 we'll have a maxima, because here all the uh, lights will get uh, constructively added, there will be a central maxima here, and at other points, suppose like P1 will have either maxima or minima depending on the relative phase difference. So I'm not going into details of the uh, derivation. So I'll just write out the condition for principal maxima and minima. Okay. So principal maxima occurs when, so suppose these slits has width of b, okay, and the distance, let's assume the slit width to be a, and uh, distance between two slits, which is the opaque distance, equal to b. Then for principal maxima we have this condition, which is a plus b sine theta is equal to n lambda, okay, where n will be 0 plus minus 1 plus minus 2 integers. Okay, so this is the condition for principal maximum. So there will be two principal maxima lying on the both side of the zero order maximum, which is at P naught. Okay, and then for minima, the condition is n a r, a plus b sine theta equal to n lambda, where n is plus minus 1 plus minus 2, so on. Okay, whole numbers. So, and this n is what? So this n is number of slits. Okay. So the minima depends on number of slits also, while maxima doesn't depend on the number of slits. Okay, so this is an interesting result, and yeah, so this is all we need for diffraction grating problems. Okay, now let's talk some about polarization, which is the second topic. We'll discuss the problems. Okay, so polarization of light can be happen in many ways. Okay, uh, you might I have discussed this Nicol prism concept, uh, uh, which polarizes the lights using this birefringence birefringence phenomena. So suppose we can make a Polaroid using such materials. So Polaroid is just a name for a material which polarizes an unpolarized light to a given in a given direction. So suppose we have an unpolarized light which have these are the electric field vectors of the light vibrating in all the direction. Okay, and this light is coming like this, and we suppose we place a polaroid material like this. Okay, so what it will do is it will polarize the light in so let's say in one direction. Okay, and if again you have this polaroid in a different direction, so suppose like this. Okay, so what will happen now is depending upon the direction relative to this grating. So suppose if this is x-axis like this and it is aligned at uh, theta, okay, related to x-axis, so then the intensity of the light will be reduced, and the direction will also change of the polarization, and the intensity with which the light is reduced is given by I equal to I naught cos square theta. This is called Miller's law. Okay. So suppose here the intensity was I naught. Here the intensity will be I naught cos square theta. And this theta is the relative angle between these two polaroids. Okay. So yeah, and then there can be polarization using reflection. Uh, so suppose you have a dielectric material like this, and this is the normal. And suppose n1 is the refractive index of uh, where the beam is incidence. So suppose this is an unpolarized light, so which has electric field vectors both in parallel and perpendicular direction. Okay, like this, and this angle is called theta t. Okay, so this angle is very special, and suppose this is the refractive n2 is the refractive index of material. So if this unpolarized light falls on this dielectric material at an angle theta p, what will happen is, and also, so what will happen, some of the light will get reflected and some of them will be refracted. Okay, and if the angle between them is 90 degree, the reflected and refracted, this reflected light will be polarized perpendicular to the direction to the direction of this plane, and this will be refracted light will be polarized parallel to the plane. Okay, so and this theta p is given by tan inverse of n2 minus n. Okay, so this polarizing angle depends on only the refractive index, relative refractive index of the material. Okay, so these concepts are used in making, so suppose sunglasses, uh, which we wear to reduce the UV exposure of the the like the glasses we use in our cars and all. Okay, window seats. So there are many application of these uh, concepts. So yeah, this is all we need for today's problems. So let's go ahead and solve some problems and remember these formulas. Okay, so our first problem today is uh, this. So the expression for maximum number of orders in a grating spectrum is given by. So, so how do you solve it? So we have this uh, expression for maximas. So which is a plus b sine theta equal to n. Here n is the order of the maxima, right? And so n is, so this is the order of the spectrum also. Now what you can do is we can invert this equation plus b sine theta by lambda. So for maximum n, this sine should be maximum, and sine theta is the maximum value of sine theta is 1. So n max is AB, since sine theta max is, okay, so D is the correct option. Okay, easy problem. Let's go to our next problem. Here we have a beam of monochromatic light incident on a plane transmission grating having 5000 lines per centimeter, and the second order spectral line is found to be diffracted at 30 degrees. The wavelength of the light is, okay. So first of all, uh, we have 5000 lines per centimeter. That means n is equal to 5000, okay, and per centimeter, that means, so how many slits will have? So we can write this as a plus b, so 1 by 5000 sorry, lines per centimeter, right? So so this is the expression for uh, a plus b, okay? Because the total number of uh, lines in 1 centimeter is 5000. Okay, so just one line will lie at 1 by 5000 uh, of the centimeter. Okay, and one line corresponds to a plus b, right? So and so now we have to find the wavelength of the line, and we know the diffracted angle 30 degree. So we can just use this formula, a plus b sine theta equal to n lambda, and the order is given, which is second. So just put 1 by 5000 sine of 30 degree is equal to 2 lambda. Lambda is equal to, so sine 30 degree is half, then 2 divided and 5000. Okay, centimeter. So this will be just 20,000 centimeter, which is uh, 1 by 20,000 of centimeter is 0.5 divided by so this is basically 1 by 2 to the power 10 to the power 4, so 0.5 by 10 to the power 4 centimeter. Correct? Yeah. So 0.5 into 10 to the power minus 7 centimeter. Sorry, this now this will be in meters. So you can write it as 5000 angstrom. Okay. So this is the wavelength of the light used. Now, third problem. The relationship between the angle of diffraction of violet and the angle of diffraction for red for a grating is. So again, this is a very simple problem. Since we have this formula A plus B sine theta equal to n lambda, and suppose everything is constant, so then theta is proportional to lambda. Okay, and uh, we know that lambda, that is wavelength of red light, is greater than the wavelength of violet light. So that's how theta for r will be greater than theta for v, right? So A is the correct answer. Now, fourth problem. Do the spectra observed by grating and prism depend on the nature of the material used? So, and the options are A for prism only, B for grating only, C yes for prism and grating, no for both. Now, you might remember uh, for prism, the deviation depends on the refractive index of the material, given as this minimum deviation. Okay, so for prism, we know that the spectra that we observe depend on the nature of the material, uh, which is due to this dependence over the refractive index of the material, the deviation angle, right? But in case of grating, uh, there is no dependence on the material. Rather, the dependence is on the uh, number of slits that we have, okay, per inch or per centimeter. So, yeah, basically, uh, for grating, spectrum is determined by number of lines, right? Nature, number of lines. So the correct option is A. Okay, only prism has this dependence of spectra of the material. Okay, so now fifth problem. What is the highest order spectrum which may be seen with a monochromatic light of wavelength 5000 angstrom by means of a diffraction grating with 2000 lines per centimeter? Okay, so here the wavelength of the light is given, right? And number of lines per centimeter of the grating is given. So number of lines are 2000 per centimeter. Okay, and so here we can calculate for, so suppose for one line, uh, for one line the length will, can be calculated as 1 by 2000 centimeter, right? Because n lines correspond to 2000, So one line will correspond to 1 by 2000. And one line correspond to A plus B, right? So now we know that the maximum highest order spectrum is observed when sine theta is 1. So n max is equal to A plus B by lambda, right? And A plus B is what? 1 by 2000, and lambda is 5000, right? And 5000 into 10 to the minus 10 angstrom. So this will be just 10 to the power 10 divided by 10 to the power 10 into 10 to the power 6, right? And also, yeah, this is in centimeters, so uh, this will be 10 to the power 8, right? So what we'll get at the end is 10. So 10 is the correct answer. Okay. Okay. Now, sixth problem. Now this problem is based on polarization of light. So here an unpolarized beam of intensity I naught falls on a polaroid. Okay, the intensity of the emergent light is. So now if you know the Miller's law, which is I equal to I naught cos theta, right? And now what we can do is, sorry, cos square theta. We can write cos square theta as half 1 plus cos 2 theta, right? Now the the polarization of light uh, by the polaroid happens. So what happens is that uh, so you can think about this polarization that I was discussing here. So let me go back to this figure. This polarization of light uh, which and this polaroid by this polaroid which makes it in a in a single direction. uh, it happens by so here the intensity is since this cos square theta the theta. So suppose between these two polarites, the theta is well defined, right? But between an unpolarized light and a single Polaroid, there is no defined angle uh, theta. So what we can do is maybe we can take the average, right? So you'll have to think about this like this. So suppose uh, this unpolarized light is coming from many polarites aligned in all the direction. Okay, and this one is one polarite, and so the angle between them varies from 0 to uh, so they can vary from minus pi to pi, right? So what we'll have to do is we'll have to take the average of this uh, quantity over all the angles, right? So maybe think about this. Uh, so what will be the average of this quantity? So we know that average of cos and sine function over a complete cycle is always zero, because so see, this is the cos. Okay, so this is one cycle, right? 0 to so 2 pi, correct? And you, as you see, uh, whatever the cos is in positive, it is in negative. So the average is 0. Same is with sine. So cos 2 theta average is 0. Thus, I is equal to simply I naught by 2. Okay, so the intensity gets half. Okay, I mean, this problem you have to think about how this intensity is getting half. I mean, you can also read about it in books. So yeah, and if you're not convinced, maybe you can tell me. I'll try to explain it a little bit more in the next meeting. Okay. Now let's go to the seventh problem. Here, the critical angle of a medium is sine inverse 0.8. This is the critical angle of a medium, and we have to find the polarizing angle. Okay. So what we can do is, so we know that critical angle is given by sine theta c is equal to 1 by mu, right? And so theta c will be just sine inverse 1 by mu. So 1 by mu is simply given here 0.8. Mu is given by 10 by 8, which is 1.25, right? And we know the expression for polarizing angle, which is just, so polarizing angle is tan theta p is mu, right? So theta p we can calculate as tan inverse mu. So tan inverse 1.25. This is the polarizing angle of this vector. Okay, so let's go to our next problem. Here, the maximum intensity in double slit experiment is I naught. Find the intensity at a point on the screen where the phase difference between two interfering beams is pi by 3. Okay, so maximum intensity is given, which is I naught. So this is a problem from our double slit experiment. Now we have to find the intensity at a point where the phase difference is pi by 3, right? Okay. So, and we have to assume that the coherent sources are used and they are of the same amplitude. So we have the formula for intensity, which is if the two waves are of same amplitude, it is given by just by this cos theta and cos phi. Right? Now, for maximum uh, intensity, this cos phi should be 0, right? So, sorry, phi is 0, right? So, I naught will be just a square plus a square plus 2a square cos 0, which is 1. So, this is 4 square, correct? Now, for any other angle, what will be the intensity? So again we can write this as, so let's take 2a square common, so we're left with 1 plus cos phi, and we can write 1 plus cos phi using trigonometric identities as 2 sorry 2a square 2a square 1 plus, so we can write cos phi as 2 cos square phi by 2 minus 1, right? So this minus 1 cancels with 1, we are left with 4a square cos square pi by 2. Okay, and now yeah, and this 4a square is our maximum intensity. So essentially I is I naught cos square phi by 2, and we know the phi, which is pi by 3, so I is equal to I naught cos square pi by 3 into 2 is pi by 6, okay, which is 30 degree, and which is cos pi by 6 is under root 3 by 2 whole square is equal to 3 by 4. So this is D is the correct answer. Okay. So yeah, this one is also simple problem. Now again a problem based on polarization. So here two polarizing sheets are placed with their planes parallel to get transmitted light of maximum intensity. Now through what minimum angle one of the sheets must be rotated to get transmitted light of intensity half of that of the previous. So this is a straightforward problem based on Miller's law. So we know that intensity, emergent intensity is given by this, right? Where I naught is the initial intensity and the theta is the angle between the two polarites. So, and we have to find this angle through which the sheet must be rotated so that we get the intensity half of that previous, that is I naught by 2, right, cos square theta. So just want to calculate cos theta, which will be simply 1 by half under root, right, and which will give us theta equal to 45 degree. Okay, so this is the correct answer. So it's a very simple problem. Now the last problem of today's session. Uh, this is based on the reflection by polarization by reflection. Now here the question is, if the reflected light from the surface of a glass plate of refractive index 1.65 is totally polarized, then calculate the refraction in the angle of refraction in the glass. Okay, so if we know the polarization formula, tan theta p is equal to mu, and refractive index is given, so tan theta p is equal to 1.65, or theta p is equal to tan inverse 1.65. Okay, if you calculate it using a calculator, you will get 58.78 degree. And I told you that if this light is polarized, then the refraction and reflected and refracted light are separated by 90 degrees. So angle of refraction will be just 90 minus angle of because this angle and this angle are essentially same, so angle of polarization is the same as the angle of reflection. So we just have to subtract this angle. The answer will be 31.22. Okay. Okay, so this is the so this is the reflected light. This is the reflected. Okay. So these are all the problems I wanted to discuss today. And so, see you guys next in the next Saturday.